Tonight's journey drifts toward Eta Carinae, a restless blue giant wrapped in its own glowing debris. Soft light moves through dust. Quiet shells expand. Hidden layers remember eruptions that shaped an entire nebula, settle in as the story glides from shimmering rims and shadowed wastes to the slow mixing of stardust across the Carinae region. If this kind of calm, science-rich sleep documentary is your style, please like the video and subscribe for more long-form cosmic stories. Now let the universe slow down. In a dense lane of the Carinae Nebula, a blue giant brightens and dims with a slow and uneasy rhythm. Eta Carinae hovers near a state where outward light pressure can lift parts of the outer atmosphere. At this distance, the star reads as a fierce core inside a pale cocoon. The cocoon is not a separate object. It is light scattered through dense gas and fresh dust. The boundary looks uneven rather than smooth. It shows gentle gradients that fade from bright to dim. It shows darker lanes where the veil is thicker. Those textures offer the first small unlock. The drama begins in the outer layers that decide how light escapes. Deep inside fusion supplies energy in a steady way. Outside that energy must pass through layers of gas. Each layer can scatter light and delay its escape. In a very luminous star, the escaping light also pushes back. Radiation pressure is the push of light on matter. It is strongest where gas is thick and light is intense. When that push grows large, the atmosphere becomes easier to unbind. A useful name marks the tipping point. The Eddington limit is a balance where light push matches gravity pull in gas. Near that limit, small changes can matter. A slight rise in opacity can trap light for longer. A slight rise in trapped light can raise the outward push. That feedback can loosen material without any sharp blast. A calm scene forms around this idea. A shifting outer boundary acts like a temporary surface. It is not a solid shell. It is a region where photons scatter many times before leaving. In that region, brightness softens into a halo. In that region, colour can change as dust forms. The halo can thicken and thin. It can tilt into arcs and asymmetries. The second small unlock follows from the shape. When the last scattering region moves outwards, the star appears larger. When it moves inward, the star appears more compact. The star can seem to breathe without any lungs. The motion is a change in where light finally slips free. An everyday analogy can stay quiet and natural. The outer layers resemble a snow cornice along a wind-carved ridge. The cornice holds for a long time. It creeps in slow silence. Cracks form inside it long before any break is seen. Then slabs can peel away and tumble. In the same way, a luminous atmosphere can shed layers in episodes. The loss matters because mass sets the star's fate. Mass is the reservoir that gravity uses to confine pressure. With less mass, confinement weakens. With weaker confinement, instability becomes easier. A major episode in Eta Carinae lasts about 20 years. That span is like the time a cave can grow a thin curtain of calcite. It is long enough for repeated pulses to add up. It is short enough to feel sudden on cosmic timescales. During such an interval, the star's apparent brightness can surge. Afterward, it can fade behind its own debris. The third small unlock is that an eruption can be prolonged. It can be luminous while still being a kind of mass loss. It is not a single flash. It is a sustained rearrangement of the outer star. Another visual anchor emerges as expelled gas expands. Material streams outward and cools. It forms broad sheets with a faint layered look. Denser knots ride inside those sheets. Each knot casts a soft shadow through the surrounding haze. Edges blur into a gradient rather than a sharp rim. That gradient comes from scattering and absorption in dust. Dust grains act like tiny screens. They redirect light and dim it. They also carry heat away as they radiate. The fourth small unlock sits inside that haze. The surrounding nebula is partly the star's own atmosphere relocated. The expelled gas carries chemistry and momentum. It becomes a moving record of what the star has lost. From close up, the record is a changing boundary. From far away, it is a growing cloud that can span light years. The scale shift is gentle but real. A thin region near the star controls escaping light. A vast region around it preserves the consequences. A limit of intuition arrives without strain. The true trigger of these giant eruptions is not fully settled. The core cannot be seen directly. The wind is thick enough to hide it. The dust is dense enough to blur it. Only indirect clues remain in the spectrum and in the changing brightness. Those clues depend on how clumpy the wind is. Clumping changes the porosity of the outer layers. Porosity changes how easily radiation pressure leaks out. That chain is hard to measure at fine detail. Distance also matters for interpretation. A modest error in distance shifts the inferred luminosity. With that uncertainty, models remain cautious. Even so, the broad picture holds. At extreme luminosity, the outer layers can become marginally bound. When conditions drift, material can depart in waves. The cocoon thickens, the halo softens. The star's light becomes filtered by its own outflow. Beyond the bright core, the Carinae Nebula supplies the larger context. Filaments curve like slow waves frozen in mist. Cold pockets and warmer cavities share the same space. In that region, dense knots of gas form and persist. Those knots set the starting point for giants like Eta Carinae. The next passage can widen to the birthplace cloud itself. It can trace how sheer mass builds a star that lives close to instability. In the Carinae Nebula, brightness and darkness share the same space in layered sheets. Eta Carinae begins as a dense pocket inside that layered cloud. At this distance, the birthplace lies about 8,000 light-years away, like a message that needs 8,000 years to arrive. The first scene is quiet and wide. Pale haze glows where gas thins. Dark lanes cut across it where dust gathers. The edges of those lanes look soft rather than sharp. A smooth gradient fades from charcoal to grey. That gradient is the first clue. The cloud is not a flat curtain. It has depth. It holds denser ridges and looser cavities in the same volume. The first small unlock follows from that depth. A massive star can only form where gravity finds a thick reservoir. The reservoir begins as a core. A core is a dense region bound by its own gravity. It is small compared with the nebula. It is still vast compared with any familiar landscape. Within the core, matter does not fall straight inward. It spirals and streams along uneven paths. Filaments act like channels. They guide gas into the centre in slow pulses. The motion stays hidden behind dust. The effect becomes visible in shape. Some ridges narrow into spines. Some spines split into forks. The forks feed separate knots. The knots sit like beads along a thread. The second visual moment settles on one knot. Its outline is darker at the centre. It lightens toward the rim. That shading suggests a peak in density. It also suggests an inward slope of temperature. The second small unlock follows. The core does not need violence to gather mass. It needs persistence. Gravity pulls. Pressure resists. In a massive core, gravity wins by a margin. That margin matters. It sets how fast the centre grows. It also sets how sensitive the system is to feedback. Feedback is the pushback from heat and light as the centre brightens. The analogy can stay ordinary and calm. The forming star resembles bread dough rising in a warm room. Bubbles grow where gas expands. Thick parts resist and thin parts stretch. The loaf changes shape without sudden snaps. In the same way a natal cloud puffs and hollows as heating increases, yet the loaf still holds dense pockets. Those pockets keep feeding the centre. The third small unlock is that growth and erosion happen together. Accretion adds mass. Radiation and wind remove mass. The balance can favour growth for a time. In that time, the centre becomes a blue giant. Light behaves as both a beacon and a force. It escapes through gaps. It also presses on dust grains. Dust grains absorb and re-radiate. That re-radiated glow warms nearby gas. Warm gas expands. Expansion opens cavities. Cavities create new paths for light. The checkpoint becomes visible as a boundary. A curved front separates dense neutral gas from a more rarefied zone. The front is not a wall. It is a layer with thickness. Its texture looks rippled. Bright rims trace the side facing the cavity. Darker backs trail behind. The fourth small unlock sits inside that rim. The nebula is being sculpted while the star is still forming. A star this luminous reshapes its cradle. The scale shift stays gentle. A dust grain can redirect a single photon. A swarm of grains can dim an entire ridge. A ridge can cast a long shadow across a glowing cavity. The shadow is not absolute. It has soft edges. Those edges come from scattering. Light bends around clumps. It also leaks through porous regions. The next visual anchor slows down to motion that is too gradual to see directly. Gas drifts along filaments. The drift thickens some strands and thins others. A strand can curve like smoke in still air. It can fold and overlap. Where strands overlap, density rises. Where density rises, gravity gathers more material. The fifth small unlock follows. Structure feeds structure. Small irregularities become larger contrasts. This is one reason massive starbirth favours crowded regions. Many cores share the same cloud. Their outflows push and compress nearby gas. Compression can trigger new cores. It can also shred old ones. The neighbourhood becomes a tapestry of competing pressures. Only a few knots gain enough mass to approach the luminous extreme. Eta Carinae sits among those rare outcomes. Another checkpoint appears as the core turns into an object that emits strongly. The surrounding gas becomes stratified. An inner zone becomes hot and thin. An outer zone remains cold and thick. Between them lies a transitional shell. That shell can show layered arcs. Each arc marks a change in density. Each arc bends around a clump like water around a stone. The sixth small unlock is that geometry records history. The arcs preserve where heating advances and where it stalls. They also preserve where dense clumps survive. Those survivors later become the seeds of complex ejecta patterns. The future instability begins with the past environment. A limit of observation enters softly. The earlier stage remains hidden behind dust. The core cannot be seen in full detail. The densest regions block visible light. The internal flows are inferred from subtle changes in emitted radiation. Those inferences depend on models of dust and gas. Those models simplify clumping and turbulence. Resolution also matters. Small knots blur into smooth lanes when viewed from far away. With that blur, estimates of mass and density carry uncertainty. Even so, the broad constraints remain reliable. A massive star must gather a large fraction of its final mass quickly. It must do so while pushing back with light. That tension sets the stage for later unrest. The closing scene returns to the larger nebula. Cavities glow like pale bowls. Dark pillars stand at their edges. The pillar tips show brighter rims. Their bases dissolve into haze. The entire region feels like a shoreline of gas and dust. The shoreline advances and retreats under changing pressure. In that shifting coastline, Eta Carinae emerges as a concentrated source. The next passage can move closer to the star itself. It can trace how the outer layers respond when radiative push nears a balance point. A bright star can look steady while its outer layers quietly shift and loosen. Eta Carinae stays near a balance where light can help lift gas away. At this distance, the star is a sharp point in the sky. Closer in, the visible boundary becomes a restless skin. It does not form a clean circle. It shows a soft edge that fades outward. That fading edge is a physical detail. It marks a region where light scatters many times. The first small unlock appears in that edge. The visible boundary is not a solid surface. It is a depth where escaping light finally turns outward. When that depth moves, apparent size and brightness can change together. A slow scene settles around the boundary. Bright patches appear like islands in a pale sea. Darker lanes separate them. The lanes are not empty. They are slightly cooler and denser. They scatter and absorb more light. The contrast stays gentle rather than sharp. It suggests mixing rather than strict layers. The next step moves inwards by a small distance. The same gas that shines also blocks. A single idea governs this behaviour. Opacity is how hard it is for light to pass. A thick fog has high opacity. A clear window has low opacity. The importance arrives at once. Higher opacity traps light longer. Trapped light builds pressure. Pressure can help push gas outward. The second small unlock is that brightness alone is not the whole story. The ease of escape matters as much as the power inside. Light behaves as a steady stream of momentum. Each scattering transfers a tiny push. One atom feels almost nothing. A vast number of atoms feels a combined force. The scale shift is quiet but immense. Microscopic scatterings add up to a global shove. In Eta Carinae, that shove can rival gravity in the outer layers. The star's luminosity is about a few million times the sun's luminosity. That is like a plain landscape lit by millions of searchlights at once. The number stays simple. The comparison turns it into an everyday weight of brightness. The next visual anchor slows down to how gas responds. The outer layers rise in broad plumes. They curve and fold back. They do not form a clean fountain. They look like slow smoke that thickens and thins. The plumes create a mottled pattern in the escaping light. Each patch is a clue. Each patch means the boundary of last scattering is uneven. The third small unlock follows from unevenness. If the boundary is lumpy, light finds easier paths. It leaks through thinner zones. It stalls behind thicker ones. That leakiness can change stability. A leaky layer can release pressure before it builds too high. A sealed layer can store pressure until it lifts. The star can alternate between these modes. That alternation can look like gentle variability. It can also set the stage for larger shedding. A single analogy can hold this mechanism without agitation. The outer layer resembles traffic at a toll plaza. Cars move smoothly when many lanes stay open. Congestion forms when lanes narrow. A brief blockage can back up the flow. When the blockage clears, the release comes as a wave. In the same way, opacity creates lane changes for photons. Thick zones slow the flow of light. Thin zones let it pass. Pressure builds where flow slows. Pressure relaxes where flow resumes. The fourth small unlock is that a star can create its own jams. Changes in temperature shift how atoms and ions absorb light. That shifts opacity. A small change can alter trapping. A small change can alter pressure. In a star near the balance point, small changes matter. Another quiet scene returns to the boundary itself. The edge shows a gradient that grows steeper at some angles. It grows softer at others. That is not a perfect sphere. It hints at outflow that is thicker in some directions. It also hints at rotation shaping the layers. Rotation is not introduced as a new term. It is a plain description of spin. Spin can flatten a star slightly. Spin can also help guide outflow into belts. Those belts can appear as subtle asymmetries in brightness. The fifth small unlock is that geometry can emerge from simple forces. Gravity pulls inward. Light pushes outward. Spin redirects what is already moving. The combined effect can favour some paths over others. From far away it looks like a bright point with a veil. Up close it is the shifting boundary with preferred directions. Limit of observation arrives without sharpness. The visible boundary cannot be directly resolved in fine detail. Distance blurs small structures into a smooth glow. Dust and dense wind add another veil. Only indirect information remains in changes of light and in spectra. A spectrum is light spread into its colours. It carries traces of temperature and motion. Yet those traces depend on how clumped the gas is. Clumping can mimic higher density. It can also hide mass in dark pockets. With limited resolution, models must guess the distribution. Those guesses can change the inferred strength of the push from light. The limit is clear. The stability threshold cannot be pinned down to a single number. It is a range shaped by uncertainty and opacity and clumping. Even with that limit, the broad mechanism stays firm. Trapped light raises pressure. Raised pressure lifts layers. Lifted layers become wind and ejecta. The sixth small unlock is that instability can be gradual. It does not require a single trigger. It can be a slow drift through conditions. A layer warms and becomes more transparent. Pressure leaks and settling follows. A layer cools and becomes more opaque. Pressure builds and lifting follows. Each cycle reshapes the boundary. Each cycle changes how bright the star appears. Another visual anchor appears in the outflow above the boundary. A thin veil streams outward. It thickens into sheets. The sheets ripple like fabric in a steady breeze. The ripples cast faint self-shadows, their edges blur into haze. That haze is where dust can form later. Dust formation is not forced here. It is a gentle mention of future filtering. The seventh small unlock is that the visible boundary and the wind are linked. A deeper boundary means thicker layers above it. Thicker layers above it mean stronger scattering. Stronger scattering means a softer halo. As the halo grows, the star's sharpness fades. The outflow becomes part of the light source. The journey can now widen to consequences. A wind shaped by uneven opacity is not smooth. It carries dense clumps and thin gaps. It can meet another wind in the system. In that meeting, shocks and arcs can carve the outflow. The next section moves into the paired nature of Eta Carinae. It follows how two winds collide and sculpt structure without any direct contact. A second light source quietly shapes the storm around Eta Carinae, without ever being seen as a clear disk. Eta Carinae behaves like a paired system whose two outflows collide and carve structure into the surrounding wind. At this distance, the space around the star is not empty. It is a moving fog of ionized gas. It streams outward in layered sheets. Some sheets are thicker, some sheets are thinner. Where thickness rises, the glow softens and the edge blurs. Where thickness falls, the glow sharpens and fades. A new scene forms inside that flow. A curved arc appears as a bright rim. It has a clean leading edge and a softer trailing haze. The rim marks a collision front where two winds meet. The first small unlock sits in the curve itself. A collision between winds does not make a flat wall. It makes a bent surface. The bend points toward the weaker flow and away from the stronger one. That geometry carries a quiet map of momentum. Colliding winds are simply two outflows that run into each other. Each wind carries mass and speed. When they meet, gas compresses and heats. A shock front is a thin region where flow changes abruptly. It is like a sharp crease in a moving sheet. The crease travels with the sheet while material slides through it. The visual anchor stays slow and specific. The bright rim looks like a crescent of frost on a dark window pane. The crest is narrow. The brightness drops quickly behind it. A faint gradient spreads outward like breath on glass. Along the rim, small ripples appear. They hint at instabilities that wrinkle the surface. The second small unlock comes from those wrinkles. Wrinkles mean the collision surface is not smooth. A smooth surface would radiate evenly. A wrinkled surface flickers with changing density. That flicker can modulate the system's brightness without changing the core. A gentle checkpoint follows the rim as it wraps through space. The rim is not fixed. It shifts as the orbit changes orientation. The orbit sets how the companion approaches and recedes. It sets how close the winds are forced to meet. The key rhythm is slow. The cycle is about 5.5 years. That is like a familiar half-decade pattern in weather records. It is long enough to feel stable. It is short enough to return within a human lifetime, even though no human appears here. The third small unlock is that a long period can still shape rapid changes. Near closest approach, density rises where winds collide. Higher density cools differently and radiates more strongly. Farther apart, the collision loosens and the rim fades. The same mechanism can explain repeating brightening and dimming. The analogy stays in nature and avoids tools. Two weather fronts can meet over a calm sea. Warm air glides above cold air. A curved band of cloud forms along the boundary. The band brightens where lifting is strongest. It thins where air streams past. In the same way, two stellar pistes form a boundary surface, though. The surface glows where compression is strongest. It thins where flow slips around the edges. The fourth small unlock follows. A boundary can create structure without any solid obstacle. Gas alone can sculpt gas. Another visual moment slows down to the interior of the collision zone. Behind the bright rim, gas expands into a wake. The wake is less dense. It looks like a cavity. The cavity is not empty. It is simply more transparent. Light escapes more easily through it. That transparency matters because the main star's wind is already thick. A locally cleared corridor can change what reaches space. The fifth small unlock is that collisions can open windows. A window does not need to be stable. It only needs to exist long enough to alter the emerging spectrum. Light behaves as a messenger. It carries fingerprints of temperature and motion. When a cavity opens, deeper layers can contribute. When a cavity closes, only outer layers dominate. The scale shift is quiet again. Microscopic ions scatter individual photons. A global cavity changes how an entire outflow appears from far away. A new checkpoint appears in the rim's shape. The arc is tighter at some phases and broader at others. That change hints at an elongated orbit. Eccentricity is how stretched an orbit is. A stretched orbit has a closer and a farther part. The importance is immediate. When distance shrinks, the collision strengthens. When distance grows, the collision relaxes. The sixth small unlock is that distance controls compression. Compression controls heating. Heating controls emitted light. The chain stays simple and calm. Another scene anchors the physical detail of motion. Clumps in the main wind drift outward like slow embers in a current. As they cross the collision front, their edges sharpen. A thin, bright outline forms. Behind them, a faint shadowed trail appears as the wake wraps around. The outline is a boundary where density jumps. The trail is a gradient where gas mixes and cools. Those features are small. They matter because they reveal flow direction. They also reveal that the wind is not uniform. The seventh small unlock arrives. A clumpy wind makes a variable collision zone. Each clump briefly strengthens the shock where it passes. Each gap briefly weakens it. The result can be a steady cycle layered with fine texture. The limit of observation enters softly and clearly. The companion is hard to isolate. The central region is shrouded in dense wind and dust. Direct imaging of the inner collision surface is limited by distance and glare. Much of the evidence comes from spectral lines and their changing shapes. Those shapes depend on viewing angle. They also depend on clumping, which is not measured directly in full detail. A model can fit the same data with different clump sizes. It can also trade density against speed. With that degeneracy, some parameters remain uncertain. The location of the collision surface is inferred rather than seen. The temperature distribution is also inferred. The uncertainty does not erase the overall picture. Two winds collide. A bent boundary forms. The boundary shifts with orbit. The eighth small unlock is that inference can still reveal structure when direct vision fails. A signal would still carry phase lock changes. Those changes would still repeat with the long period. Another visual anchor returns to the crescent rim as the system moves through a quiet phase. The rim softens. The wake broadens, the cavity becomes less distinct, the surrounding wind takes over again. It resumes a more spherical haze with gentler symmetry. The glow becomes smoother. The sharpest edges fade into a wide halo. The scene feels like a tide withdrawing. It leaves faint lines where the boundary had been. The closing transitions without suspense. The next section can follow the wind itself as a sculptor. It can trace how steady outflow builds layered debris that later hides and reveals the star in turn. A wind can be gentle in appearance while carrying away a star's future in slow layers. Eta Carinae releases a dense stellar wind that both hides the star and builds a record of loss. At this distance, the outflow reads as a pale glow around a bright core. Closer in, that glow becomes a moving skin of gas. It streams outward in sheets and knots. The sheets overlap like translucent veils. The knots drift within them like darker beads. The edge of the glow does not end sharply. It fades through a smooth gradient where scattering weakens. That gradient is the first physical detail that matters. It marks where light stops bouncing often. It also marks where the wind becomes more transparent. The first small unlock follows from that fading edge. A thick wind can act like an extended atmosphere. The star's apparent boundary becomes a region rather than a surface. A calm scene forms where the wind is densest. Near the source, brightness looks milkier. Farther out, it becomes thinner and dimmer. Narrow streaks appear where density rises. Between them, faint gaps appear where density falls. Those gaps are not empty. They are corridors of lower opacity. Light behaves as a stream that prefers the easiest corridors. That preference shapes what escapes. The main idea stays simple. A stellar wind is gas flowing outward from a star, is driven by radiation and pressure in outer layers. In Eta Carinae, the wind is unusually heavy. It carries enough material to form a shroud. The second small unlock follows at once. The same outflow that removes mass also filters light. Mass loss is not only a future concern, it changes the present appearance. Another visual anchor settles on a thin shell in the wind. A faint arc appears like a curved seam. It is brighter on the inner side, it is softer on the outer side. The seam suggests a density enhancement that has expanded outward. It resembles a tide line on a rocky coast after calm surf. The line is not a hard border. It is a band where small grains and gas cluster. The analogy stays natural and slow. Tides leave layered marks. Each mark records a different water level. In the same way the wind can leave layered density bands. Each band records a slightly different outflow state. The third small unlock is that a steady wind can still be structured. It does not need an explosion to form shells. Small changes near the star can imprint rings and arcs far away. A gentle scale shift emerges. A tiny change in opacity near the source can alter the wind's push. That change then travels outward for years. Over that time it expands into a shell that spans vast distances. A single photon scatter is microscopic. A shell's faint arc is enormous. The next checkpoint moves into the wind's texture. The wind is not smooth. It is clumpy. Clumps are denser pockets embedded in thinner flow. The clumps matter because density controls cooling. Density also controls how strongly light is absorbed and scattered. The fourth small unlock follows. A clumpy wind can appear denser than it truly is. It can also hide mass in compact pockets. This changes how mass loss is inferred. The scene slows to a clump crossing a brighter background. Its leading edge looks sharper than its trailing edge. A soft shadow forms behind it as light scatters around. The shadow has a gentle taper. It fades gradually into the haze. That taper is a physical sign of mixing. Mixing blurs the clump into the flow. Over time, the clump stretches. It becomes a filament. The filament curves slightly as surrounding gas streams past. The fifth small unlock is that clumps become threads. Threads become sheets. Sheets become shells. The wind converts small structure into larger structure as it expands. A single number can anchor the wind's motion. The outflow speed is about 500 kilometers per second. That is like a storm front that can cross the diameter of Earth in under half a day. The number stays rounded. The comparison makes the pace tangible. The scale shift is quiet again. Near the star, acceleration happens over a small region. Far from the star, the wind coasts for years as it builds the halo. The next checkpoint follows how the wind meets itself. Faster parcels can catch slower parcels. When they meet, compression forms. Compression can create thin shells. Those shells can cool. As they cool, they become better at forming dust. Dust is tiny solid grains that absorb and scatter light. Dust is not always present near the star. It forms where temperatures fall enough for solids to survive. The sixth small unlock is that dust can appear far from its source. It can then dim the star without touching it. Another visual anchor appears in the outer halo. A faint bowl-shaped glow forms on one side. On the opposite side, the glow looks slightly flatter. The difference suggests the wind is not identical in all directions. The brightness changes with angle because column density changes with angle. Column density is how much material lies along a line of sight. A thicker column scatters more light. A thinner column scatters less. The seventh small unlock follows. Geometry can be inferred from brightness alone. A signal would carry more scattered light through thicker columns. It would carry a clearer view through thinner ones. Yet the inference is limited by what cannot be seen directly. The inner wind region is opaque. It hides where the wind is launched and shaped. The clumps are too small to resolve at great distance. The observed glow blends many clumps into one smooth haze. Spectral lines help, yet they also blend. They depend on ionization state and temperature. Those states vary through the wind. Models must assume a distribution of clump sizes. They must assume how porous the wind is. Different assumptions can fit the same data. This is the limit of observation. The mass loss rate cannot be pinned down uniquely. The wind speed can be estimated more reliably. The exact amount of mass carried each year remains uncertain. Even with that uncertainty, the broad mechanism remains firm. A dense wind expands and cools. It forms shells and filaments. It can carry dust that filters light. It removes mass that the star cannot easily replace. The eighth small unlock is that uncertainty in detail does not erase the overall direction. Over time, repeated outflow reshapes the surroundings. The halo thickens in places. It thins in others. The star's light becomes a mix of direct and scattered paths. The scene returns to the faint arcs in the wind. Each arc drifts outward and broadens. Its inner edge stays brighter for a time. Its outer edge dissolves into a gradient. The arcs become quiet markers of episodes. They set the stage for a much larger episode. When conditions push beyond gentle variability, the outflow can surge into something closer to an eruption. The next section moves into that turning point. It follows how a prolonged brightening can launch an enormous mass of material into the surrounding nebula. A star can brighten for years and still be in the act of throwing matter outward. Eta Carinae enters a prolonged eruption where light and mass loss rise together. At this distance, the event is remembered as a long swell rather than a single flash. The space around the star thickens, the inner glow turns softer, the outer halo gains new layers. The first visual anchor is a broad, expanding curtain of gas. It looks like a pale dome with a darker waist. Its inner edge is brighter. Its outer edge fades into a smooth gradient. That gradient marks thinning density and weaker scattering. The first small unlock sits in the curtain's shape. A prolonged eruption can build a shell that keeps its geometry. Geometry survives because expansion is fast compared with later mixing. The next checkpoint moves inward to the cores that can be described safely. The outer layers reach a state where radiation pressure can lift them. The lift does not need to be steady. It can arrive in surges. A surge thickens the wind. A thicker wind traps more light. Trapped light increases the outward push. The chain stays quiet and circular. It is feedback rather than a single trigger. The second small unlock is that the eruption can be self-sustaining for a time. It feeds on opacity changes in the outflow. A simple term can appear and be defined once. A super Eddington phase is when light push exceeds gravity in layers. It lasts only where opacity is high. It does not mean the whole star is unbound. It means the outer skin can be lifted more easily. The analogy stays gentle and unique. The atmosphere resembles a sand dune face under a steady wind. Grains creep upward in slow motion. A small gust steepens the slope, then a sheet of sand slides down and resets the face. In the same way, a luminous skin can creep toward a threshold. A change in opacity can push it over. A layer then departs and the balance resets. The third small unlock follows at once. The eruption can be a series of layer losses that look continuous from far away. A new visual moment slows down to fine structure within the curtain. Thin filaments appear like faint ribs in the expanding dome. Between ribs, dimmer lanes stretch. The ribs are denser. They scatter more light. The lanes are thinner. They let light pass more directly. The ribs curve with the flow. They keep a slight symmetry across the waist. This is a physical detail that matters. Symmetry implies a preferred direction in the outflow. It can come from rotation or from a companion shaping the flow. The fourth small unlock is that outflow remembers the conditions of launch. The memory is written into density, contrasts, and curvature. A single number can anchor the timescale. The brightest phase lasts about 20 years. That is like the span of a tree growing a thin new ring. It is long enough for repeated surges to stack into thick debris. It is short enough to feel sudden against stellar lifetimes. The scale shift stays calm. Seconds matter for photon scatterings. Years matter for shell growth. Millions of years matter for the star's whole life. The fifth small unlock is that the eruption is brief only in a cosmic sense. It is long in the life of surrounding gas. The next checkpoint follows the expanding material as it cools. Cooling is not just a drop in temperature. It is a change in what can exist. When gas cools, atoms recombine. When recombination increases, opacity can change again. Dust can also begin to form in cooler zones. Dust grains survive where radiation is less harsh. They add a new kind of filtering. Light behaves as a softer glow after repeated scattering on dust. The dome's outer edge becomes more diffuse. The waist becomes darker as column density rises along that line. The sixth small unlock is that dust can turn brightness into concealment. The eruption can make the star harder to see later. Another visual anchor appears at a larger radius. A thin outer shell separates from the main curtain. It is faint but coherent. Its leading edge is sharper. Behind it a softer trail follows. That indicates a faster parcel catching up to older material. When a faster parcel catches a slower one, compression forms. Compression forms thin shells. Thin shells can be brighter because density increases. The seventh small unlock follows. Brightness changes can arise in the outflow itself. They are not only changes in the star. The journey now touches the limit of intuition and measurement. The inner launch region cannot be directly resolved. The eruption's mass is inferred from emitted light and from spectral signatures of moving gas. Those signatures depend on clumping and dust. Clumping can hide mass in dense pockets that contribute little light. Dust can absorb light and re-radiate it at other wavelengths. With distance and glare, small-scale structure blurs. Models must choose a distribution of clump sizes. Different choices can yield different mass estimates. This is the limit of observation. The exact amount of mass expelled remains uncertain. The broad conclusion remains stable. A very large amount of material leaves compared with normal winds. The eighth small unlock is that uncertainty in quantity still leaves certainty in kind. The event is an eruption in the outer layers. It rearranges the surrounding space on a huge scale. A final visual scene returns to the dome and its waste. The waste looks like a thick belt of darker haze. Above and below it, the shell appears puffed and brighter. The edges of the lobes remain smooth. They fade into the nebula with a gentle gradient. The whole structure drifts outward. It carries momentum like a slow expanding breath. The closing transition stays soft and forward-looking. The next section can focus on the aftermath that becomes easiest to see. It can follow the bipolar shell that preserves the eruption's geometry in long-lived dust and gas. The aftermath of a long eruption can become a shape that stays visible long after the brightening fades. Eta Carinae leaves behind a bipolar shell that preserves the direction and layering of the outflow. At this distance, the shell appears as two opposing lobes with a darker waste between them. The lobes look inflated and smooth. Their edges show a sharper rim that softens into haze. The waste looks like a thicker band where light dims more strongly. That contrast is the first small unlock. A single eruption can produce different densities in different directions. The geometry is not an ornament. It is a record of where gas escapes most easily and where it is blocked. The main visual anchor settles on the lobe rims. Each rim is thin compared with the lobe size. It brightens on the side facing the central glow. It fades on the far side through a gentle gradient. That gradient comes from scattering in dust and gas. Some parts of the rim show faint striations. They look like shallow grooves running along the surface. Those grooves mark layers within the shell. The second small unlock follows. Layering means the eruption is not one smooth breath. It is a sequence of surges that stack into a thin wall. A calm checkpoint moves to the waist where the shell narrows. The waist is not empty space. It is a denser skirt of material. It blocks and redirects light. It also creates a shadowed lane across the middle. The shadow is soft at its edges. It becomes darker toward the center. That shading is a physical detail that matters. It implies a thick column of dust and gas in the equatorial plane. The shell, therefore, has two parts. A polar outflow forms the lobes. An equatorial outflow or compression forms the waist. The third small unlock is that a single event can separate into channels. Some material escapes towards the poles, some gathers around the middle. Two concepts can carry the rest of the section. The first is expansion. The shell grows larger as material coasts outward. The second is scattering. Dust grains redirect light and create the glow and gradients. The expansion is slow enough to seem stable. It is still fast on stellar timescales. The shell spans about 1 light year across. That is like a circle that light needs about a year to cross. The number anchors the scale without forcing detail. The scale shift follows gently. Motions near the star unfold over days and years. The shell then persists for centuries as it drifts outward into the nebula. Another visual scene forms inside the lobes. The interior looks hollow. The glow is stronger along the rim than in the center. This is not because the interior is truly empty. It is because the line of sight through the rim crosses more material. More material means more scattering. The fourth small unlock is that brightness can be a path length effect. A thin wall can outshine a thicker interior if the view passes through a longer slice of it. This is the quiet power of geometry. The analogy stays ordinary and unique. The shell resembles a pair of soap bubbles pressed together. The contact region forms a narrow belt. The outer surfaces remain smooth. Light catches the curved skin more strongly at some angles. The bubbles look brightest along their edges. The resemblance is not perfect. The lobes are not fragile films. The analogy still helps. It turns an abstract three-dimensional shell into a familiar curved surface. The fifth small unlock follows. If the shell is thin, small changes in thickness create strong visual changes. A slight ridge can create a brighter seam. A slight gap can create a dimmer lane. The next checkpoint follows the shell's seams. Along each lobe, faint ribs appear. They run from the waist toward the tip. The ribs are subtle. They suggest that outflow is not uniform even along the pole. Dense strands ride within a thinner sheet. As the shell expands, those strands stretch into long arcs. Their edges blur into a fine haze. The haze is dust-rich. It scatters light forward and sideways. Light behaves as if it is softened by many small turns. The sixth small unlock is that dust can turn a violent history into a calm glow. Dust is not introduced as a new burden of jargon. It remains a simple actor. It absorbs and re-emits. It also redirects. This is why the shell can appear luminous even when direct light is partly blocked. Another visual anchor appears at the lobe tips. Each tip is rounder than the waist. The rim there is thicker. The glow spreads wider, then fades into the surrounding nebula. The boundary does not end in a crisp line. It dissolves through a gradient. That dissolution is the physical signature of mixing. The shell meets older gas and begins to share momentum. The seventh small unlock is that the shell is both an object and a process. It is an expanding structure. It is also a region of ongoing interaction with the environment. The environment in Carinae is not still. It contains filaments and cavities. As the shell expands, it encounters uneven density. In denser zones, it slows slightly and thickens. In thinner zones, it keeps a more even curve. This unevenness can leave subtle asymmetries. One side can look brighter, another side can look smoother. The cause is not a change in the eruption itself. It can be a change in what the shell runs into. The eighth small unlock is that context shapes appearance. A single shell can look different in different directions because the medium is different. A limit of observation enters softly and clearly. The true three-dimensional shape is inferred from projected light. The viewing angle is not measured directly. It is estimated from symmetry and motion. Dust complicates the picture. Dust grains of different sizes scatter light differently. A model can trade grain size against total mass. It can trade clumping against thickness. With limited resolution, small clumps merge into a smooth glow. With strong extinction, the far side can be hidden. This is the limit of observation. The shell's exact mass distribution remains uncertain. The waist can be denser than it appears if it is very opaque. The inner regions can hide additional layers. Even so, the broad structure is robust. Two lobes exist. A waist exists. A thin shell expansion exists. Those features are supported by the rim brightening and the interior dimness. They are supported by the layered seams and gradients. The ninth small unlock is that a stable outline can be trusted even when internal details are uncertain. The section returns to the quiet glow of the shell in the surrounding nebula. The lobes drift outward. Their rims remain the brightest edges. The waist remains the darkest band. The whole form becomes a slow lantern of dust and gas lit by filtered starlight. The transition stays gentle. The next section can move closer to the grains that make the glow. It can follow how dust condenses, survives, and scatters light into soft gradients. A nebula can glow softly because countless tiny grains turn harsh starlight into a gentler haze. Dust in Eta Carinae's ejectiforms survives and then controls what the system looks like from far away. At this distance, the bipolar shell appears brighter along its rims and dimmer through its waist. That contrast is not only geometry, it is also dust acting like a filter. The main visual anchor is a thin luminous rim with a darker interior. Along the rim, brightness peaks in a narrow band. Just inside it, the glow falls off through a smooth gradient. The gradient is a physical detail that matters. It signals scattering and absorption changing with depth. The first small unlock follows from that gradient. Dust does not simply block light, it reshapes light into a softer distribution across space. A calm checkpoint moves to the smallest scale without losing the lull. Dust grains are tiny solids that float in gas. They can be made of carbon-rich or silicate-rich material. They form when gas cools enough for atoms to stick. They survive when radiation and collisions do not destroy them too quickly. A single grain is microscopic. Yet a cloud of grains can dim a star and brighten a shell. Light behaves as if it is wading through a mist. Each encounter can redirect it. Some light is absorbed and later re-emitted as heat. Some light is scattered and sent along new paths. The second small unlock is that dust creates both darkness and glow in the same act. Where dust is thick, direct light fades. Where dust is arranged in a thin shell scattered, light can outline the shell. An everyday analogy can keep the idea grounded and unique. The dust layer resembles flour suspended in air above a countertop. When a lamp shines through a bright veil appears. The beam becomes visible. The edges of the beam soften. The light looks spread out rather than sharp. In the same way dust makes the star's light visible as structure. It turns invisible space into a softly lit volume. The third small unlock follows. If dust is uneven, it imprints texture on the glow. The shell's seams and ribs can appear stronger where grains are denser. The checkpoint returns to the shell's waist. The waist looks darker and thicker. The darkness suggests higher column density along that band. Column density is how much material lies along a line of sight. Higher column density means more extinction. Extinction is the combined effect of absorption and scattering out of the line of sight. The term can be defined simply and left. Extinction is dimming by dust and gas along a path. The fourth small unlock is immediate. A darker waist does not prove less material. It can mean more material. It can mean a longer path through dust. This is why a thin rim can shine while a thick belt looks muted. Another visual moment slows to the lobe interior. The interior looks faint and hollow. Faintness there can come from lower path length through the shell. It can also come from grains being cooler and emitting less invisible light. The glow is therefore a mixture of scattered and re-emitted light. The scale shift is calm again. A grain absorbs energy in a fraction of a second. A shell retains the imprint of that energy over centuries. The fifth small unlock follows. Fast microscopic physics becomes slow macroscopic appearance. A single number can anchor grain size without forcing details. Typical grains are about 1/10 of a micron across. That is like a speck far smaller than a smoke particle. The number stays simple. The comparison turns it into an everyday sense of tiny. At this size, grains scatter shorter wavelengths more effectively than longer ones. This can change colour and contrast. It can also change which parts of the shell stand out. Another checkpoint follows the life of a grain. It forms in cooling gas. It then faces harsh radiation from the star. Some grains survive because they are shielded inside denser clumps. Some survive because they reside farther out where light is diluted. Some are destroyed by shocks and collisions. The sixth small unlock is that dust survival depends on hiding places. Clumps are those hiding places. In a clump, the outer skin absorbs the strongest radiation. The inner region stays cooler. Dust can persist there. The visual anchor shifts to clumps embedded in the rim. Tiny dark knots appear against a brighter band. Each knot has a brighter edge and a dimmer center. The edge marks higher scattering. The center marks stronger absorption. Behind the knot, a soft shadow trails into the haze. The shadow fades through a gradient rather than a line. That is the physical signature of diffuse scattering. The seventh small unlock follows. Shadows in dusty gas are not crisp. They are feathered by multiple scatterings. That feathering tells how porous the medium is. The next checkpoint moves to what dust hides. The central star is often not seen directly in visible light. Its light is partly absorbed and partly scattered. What reaches far away is a blend of direct and indirect paths. A signal would therefore carry delayed routes. Scattered photons take longer paths. They arrive later than direct photons. On short timescales, this can smear variability. On long timescales, it can preserve echoes of bright phases. The eighth small unlock is that dust can act like memory. It stores brightness in geometry and releases it as scattered glow. The limit of observation arrives softly and clearly. Dust properties are not measured by direct sampling. Grain sizes and compositions are inferred from how light reddens and dims. Different mixtures can produce similar reddening curves. Clumping adds another uncertainty. A smooth dust distribution and a clumpy one can look alike at low resolution. Temperature also matters. Emission depends on grain temperature, which is inferred rather than measured directly. With distance and blending, small-scale variations disappear. This is the limit of observation. Dust mass estimates carry model dependence. The exact fraction of carbon-rich versus silicate-rich grains remains uncertain. Even so, the broad roll is solid. Dust controls extinction. Dust controls scattering. Dust shapes the visible shell. The ninth small unlock follows. Even without perfect grain knowledge, the presence of dust is evident from gradients and shadows. Another visual scene closes the section gently. The rim glows like a thin lantern ring around a darker interior. The waist remains a muted band. The lobes fade into the Carinae Nebula through soft gradients. The entire structure looks calm and balanced. Yet it is made from debris of extreme mass loss. The transition remains soft. The next section can follow the colliding winds again at a larger scale. It can trace how shocks and cavities influence where dust forms and where it is destroyed. A collision between winds can be quiet at great distance and intricate up close. Eta Carinae's colliding outflows create shocks and cavities that control where gas cools and where dust survives. At this distance, the bipolar shell remains the largest landmark. Within it, smaller structures keep shifting with the long orbital rhythm. The main visual anchor is a spiral-like wake carved into the surrounding wind. It appears as a faint curved ribbon that wraps outward. The ribbon is brighter along its inner edge. Its outer edge dissolves into a smooth gradient. The gradient is a physical detail that matters. It marks a gradual change in density and temperature behind a moving shock. The first small unlock follows from the ribbon's curve. A changing orbit can draw a repeated pattern into a steady outflow. The outflow becomes a canvas. The orbit becomes a slow brushstroke. A checkpoint moves inward to the collision itself. Two winds meet and compress. The compressed zone heats. It then cools as it expands. A shock is the thin region where that compression happens. The shock is not a wall of solid matter. It is a moving boundary in gas. On one side, gas streams fast. On the other side, gas is slower and denser. The second small unlock appears immediately. Shocks can create structure without any explosion. They can carve cavities and rims through steady flow. Another quiet scene forms near the apex of the collision zone. The surface there is curved. It is sharper where pressure is highest. It is softer where flow slips around. Along the surface, small ripples grow and fade. The ripples are wrinkles in the boundary. They arise because dense gas and thin gas slide past each other. Where a ripple thickens, cooling can proceed faster. Where a ripple thins, heating can persist. The third small unlock follows. Instabilities can decide where dust can form later. Dust prefers cooler and denser pockets. It avoids hotter and more rarefied corridors. The analogy remains natural and unique. The collision zone resembles a river, meeting a sandbar at an angle. The current splits. One branch scours a deep channel. Another branch deposits a pale ridge of sand. The ridge is never still. It shifts with each pulse of flow, in the same way a colliding wind zone scours cavities and piles up compressed arcs. The fourth small unlock is that the system produces both clearing and piling at once. Clearing creates transparent windows. Piling creates dense lanes that scatter light. The next checkpoint introduces the one number that sets the rhythm. The cycle repeats about every 5.5 years. That is like the cadence of a slow seasonal pattern returning after half a decade. The number is rounded and spoken cleanly. The scale shift remains gentle. Inside the collision zone, gas responds in hours and days as it cools. Farther out, the carved ribbon expands for years before it blends into the nebula. Over centuries, the bipolar shell preserves the record of older phases. The fifth small unlock is that multiple clocks run at once. A short clock sets cooling. A medium clock sets orbital shaping. A long clock sets the persistence of ejecta. Another visual anchor appears in the wake's spacing. The curved ribbon shows repeated arcs. Each arc is slightly offset from the next. The offset follows the orbit. The arcs are thinner where density is lower. They are thicker where compression is stronger. Their brightness peaks along the same side each time. That asymmetry hints at a preferred viewing angle through the wind. The sixth small unlock follows. Even without seeing the inner region directly, repeated arcs can reveal the hidden motion. Light behaves as a tracer. It brightens where density and temperature favour emission. It dims where extinction rises. In the collision zone, temperature can be too high for dust survival. Farther downstream, gas can cool enough for grains to persist. The wake therefore has zones. Close to the collision apex, gas is hotter and dust is fragile. Downstream, gas is cooler and dust can endure. The checkpoint becomes visible as a change in texture. Near the apex, edges look sharper and smoother. Downstream, the ribbon becomes fuzzier. The fuzziness comes from scattering by dust mixed into the flow. The seventh small unlock is that softness can be a signature of dust. The presence of dust does not always announce itself as a dark lane. It can also appear as a halo that broadens edges. Another scene forms at the boundary of a cavity. The cavity is a region of lower density carved by the faster wind. Its interior looks dimmer. Its boundary looks brighter. The boundary forms a thin rim. The rim casts a faint shadow into the denser wind behind it. The shadow has feathered edges. It fades through a gradient. That feathering is a physical sign of multiple scatterings. The eighth small unlock follows. A cavity can act like a funnel for light. It can let a clearer beam escape in a narrow direction. At other angles, dust and gas scatter and absorb more strongly. The system's appearance therefore depends on direction. The same intrinsic changes can look stronger or weaker. A signal would carry phase-locked variations. It would also carry smearing from scattered paths. This keeps the variability calm rather than abrupt. A limit of observation arrives softly and clearly. The inner shock region is too compact to resolve in full detail. Distance blends the apex and downstream zones into one blurred core. Dust adds extinction that hides the far side. The wake pattern is inferred from subtle brightness changes and spectral signatures of motion. Those signatures depend on models of clumping. Different clump sizes can mimic different cooling rates. A model can trade density against filling factor. With that degeneracy, some internal parameters remain uncertain. The exact temperature distribution is inferred rather than mapped directly. The exact dust formation sites are also inferred. This is the limit of observation. Only indirect evidence guides the picture. Even so, the broad geometry is stable. Two winds collide and compress. Shocks carve cavities. Downstream cooling allows dust to persist. The ninth small unlock is that a consistent pattern can be trusted even when the smallest scales remain hidden. The section returns to the larger shell where these inner patterns are embedded. The wake arcs drift outward and widen. Their contrast softens as mixing grows. The bipolar lobes remain the calm outer frame. Inside that frame, the collision zone continues to etch faint ribbons that fade into haze. The transition remains gentle and forward-looking. The next section can move inward again. It can focus on internal instabilities in the star's outer layers that feed the wind and set the conditions for future surges. A giant star can store energy in its outer layers and release it in slow pulses that feel like breathing. Eta Carinae's envelope becomes unstable when energy transport and opacity fall out of step. At this distance, the inner star remains hidden behind dense wind and dust. Only the outer signs can be followed. The first visual anchor is a shifting boundary of light around the star. It looks like a pale lip that brightens, then drifts outward. Behind it a dimmer trough follows. The edge is not sharp, it fades through a smooth gradient where scattering weakens. That gradient is a physical detail that matters. It reveals how the last scattering region moves through layers of changing density. The first small unlock follows immediately. The star can look larger when light escapes from farther out. The star can look smaller when light escapes from deeper in. The next checkpoint moves into the idea that controls this sliding boundary. Opacity is how strongly gas blocks light. In a luminous envelope, opacity is not fixed. It changes with temperature and ionization. A small change can trap longer. Trapped light raises pressure in the same layer. Higher pressure lifts the layer outward. Lifted gas expands and cools. Cooling can change opacity again. The second small unlock is that a soft feedback loop can form. It can keep the envelope hovering near a threshold. Another scene settles into the texture of the lifted layer. The lifted gas does not rise as a smooth sheet. It forms rolling cells and broad plumes. Their tops look brighter. Their bases look slightly darker. The contrast is gentle but persistent. The plumes create a mottled glow that drifts across the boundary. That drift suggests motion without any clear rotation pattern. The third small unlock follows. Even without a violent eruption, the envelope can rearrange itself continuously. A simple term can appear once and stay light. An opacity bump is a layer where light blocking suddenly increases. The definition is brief and then released. Such a layer can act like a temporary dam for energy. Energy arrives from below. It pauses and builds pressure. When the layer shifts or thins, the stored push can lift material outward. The analogy remains natural and unique. The envelope resembles a winter pond with a thin ice lid. Water below keeps moving. Heat gathers under the lid. The surface holds until cracks spread. Then the lid flexes and settles into a new shape. In the same way, a high opacity layer can hold back energy. Pressure can flex the layer outward. Then the layer can thin and relax. The fourth small unlock is that an instability can be cyclic without being regular. The cycle depends on how quickly energy leaks through. It also depends on how quickly lifted gas cools and recombines. Light behaves as both cargo and force during this cycle. When light is trapped, it contributes more pressure. When light escapes, pressure drops and settling follows. A single number can anchor the timescale in a safe way. In the densest parts of the outflowing envelope, light can take about a week to diffuse outward. That is like a dye plume taking about a week to spread across a still pond. The number is rounded and gentle. The comparison turns delay into a familiar slowness. The scale shift follows quietly. Individual photons scatter in tiny steps. Many scatterings add up to days of delay. Those days can shape years of observed variability because the envelope responds over time. The fifth small unlock is that brightness changes can lag behind internal changes. The envelope does not react instantly, it stores and releases. Another visual moment anchors the idea of storage. A faint nested set of translucent layers surrounds the central glow. Each layer is slightly brighter on its inner side. Each layer fades outward through a gradient. The spacing is not perfectly even. Some layers look compressed, some look stretched. This layering is not a rigid stack, it is a moving pattern of density enhancements. The sixth small unlock follows. Layering means the outflow carries a memory of past pulses. Each pulse leaves a thin enhancement that expands and thins. Over time, these enhancements can merge into shells farther out. The next checkpoint touches the consequence for mass loss. When a layer lifts, the wind can thicken. A thicker wind increases scattering. Increased scattering softens the light and enlarges the apparent halo. When the layer settles, the wind can thin. The halo shrinks and the star looks clearer in some directions. The seventh small unlock is that instability modulates the wind as much as it modulates brightness. This is why the system can switch between clearer and more veiled phases. A limit of intuition and observation arrives softly. The deep layers that seed the instability cannot be seen directly. The central source is shrouded by its own wind. Dust further dims and reddens light along some paths. Variability is measured in integrated brightness and in spectral line changes. Those clues are indirect. They depend on assumed geometry and clumping. A smoother wind and a clumpier wind can produce similar light curves. A larger apparent radius and a higher opacity can also mimic each other. This is the limit of inference. Models can trade one property against another. The exact depth of the opacity bump and the exact amplitude of lifting remain uncertain. Even so, the broad mechanism stays stable. Opacity changes can trap light. Trapped light can raise pressure. Pressure can lift layers and thicken the wind. The eighth small unlock is that a few linked ideas can explain many surface signs. Another visual anchor returns to the shifting lip of light. It drifts outward, then slows. Its brightness peaks along a thin rim. Behind it, the trough becomes darker for a time. Then the contrast softens as mixing spreads the gradient. The motion feels like a slow-tiding gas rather than a sharp wave. The final checkpoint widens to the outer debris. Pulses in the envelope do not vanish. They travel outward in the wind. As they expand, they become faint shells and arcs. Later, faster parcels can overtake them and compress them into brighter seams. The closing transition remains gentle. The next section follows how older layers meet newer outflow. It traces how shells ripple and stack as the system continues to shed mass into the surrounding nebula. A star's past can continue moving outward long after the star appears calm again. Eta Carinae's older shells meet newer wind and turn smooth expansion into layered ripples. At this distance, the bipolar lobes remain the largest silhouette. Around and within them, faint arcs drift like slow rings in fog. The main visual anchor is a nested set of thin shells that resemble overlapping ripples on a quiet lake. Each ripple is not a perfect circle. It is a curved arc with a brighter inner edge. The outer edge fades into haze through a smooth gradient. That gradient is a physical detail that matters. It signals a gradual decrease in density behind a compressed front. The first small unlock follows. A shell can stay visible because compression concentrates material into a thin wall. The wall scatters and emits more strongly than the space around it. The next checkpoint moves into the simple mechanism that creates these ripples. A faster wind can catch a slower layer. When it catches, gas compresses. Compression forms a thin shell. The shell then expands outward as a unit while material continues to flow through it. This is not a rigid bubble. It is a moving boundary. The second small unlock is immediate. A boundary can travel even when the gas inside it keeps changing. Another quiet scene forms where a new wind front reaches an older layer. The older layer is thicker and cooler. It is also more clumpy. The new wind is thinner and faster. At the meeting point, a narrow bright rim appears. Behind it, a softer wake spreads. The rim is slightly corrugated. It shows tiny scallops along the edge. The scallops mark instabilities that grow where shear and cooling compete. The third small unlock follows. Instabilities add texture, yet the shell still holds a coherent arc. The overall arc therefore encodes the bulk motion. The fine scallops encode local mixing. A single concept can keep the story focused. Momentum is mass times speed in plain language. When a faster parcel hits a slower parcel, momentum must be redistributed. The faster parcel slows. The slower parcel accelerates. The combined material can form a new speed in between. The shell is where that redistribution occurs. The analogy stays ordinary and unique. The interaction resembles a snowplow pushing fresh snow along a road. The plow itself does not need to be imagined as a tool. The idea can be framed as a moving ridge of snow driven by wind along a frozen plain. Loose snow drifts forward and piles into a ridge. The ridge gathers more snow as it moves. It thickens at the front. It leaves a thinner trail behind. In the same way, a wind-driven shell gathers older material into a ridge. The fourth small unlock follows. A shell can grow more massive as it travels. It becomes a collector of the past. The checkpoint widens to the timescales that make this possible. The oldest visible shells from the Great Eruption are about 2 centuries old. That is like a tall tree carrying 200 growth rings in its trunk. The number stays simple and spoken cleanly. The scale shift is calm. A photon crosses the shell in moments. A shell crosses a fraction of a light year in centuries. Over that time, the star's wind keeps changing. Each change sends a new layer. Each layer eventually meets older material. The fifth small unlock is that time stacking creates structure. The nebula becomes an archive. Another visual anchor appears as the shells overlap. 2 arcs cross at a shallow angle. At the crossing, brightness increases. The increase is not a new emission source. It is a path length effect. The line of sight passes through more compressed material where arcs overlap. The overlap region looks thicker. The edges there appear sharper. Outside the overlap, the arcs look thinner and softer. The 6th small unlock follows. Some bright knots can be purely geometric. They do not require extra mass. They require aligned layers. The next checkpoint moves to dust and cooling within shells. Older shells are cooler. They can host dust grains and molecules. Newer wind is hotter and more ionized. When new wind meets old shell shocks can heat local zones. Heated dust can briefly glow more strongly in some wavelengths. Invisible light dust mostly sutties and extinguishes. In other bands it can emit. The important point stays calm. Shells can be both shields and radiators. The 7th small unlock is that dust distribution can change the shell's apparent thickness. A dust-rich section can look darker in direct light. It can look brighter in scattered light along a rim. The same material can hide and reveal depending on angle. Another scene centers on a cavity carved by the colliding winds. The cavity is a region of lower density. It allows newer wind to stream more freely in a preferred direction. When that stream hits an older shell, the shell brightens along a narrow segment. The segment looks like a crescent cut from a larger ring. Its ends fade into haze. The fade is gradual. It indicates the stream does not strike uniformly. It strikes strongest along a line. The 8th small unlock follows. Directional outflow can light up only part of a shell. This creates the impression of disconnected arcs. The arcs are not separate objects. They are segments of a larger structure. A limit of observation arrives softly and clearly. The full 3-dimensional arrangement cannot be seen directly. Shells overlap along the line of sight. Distance blends thin fronts into broader bands. Dust extinction hides parts of the far side. The relative speeds are inferred from Doppler shifts in spectral lines. Those shifts depend on assumed geometry and clumping. A thicker shell seen edge-on can mimic a thinner shell seen face-on. With limited resolution, small ripples merge into smooth rims. This is the limit of reconstruction. The exact layering order can be ambiguous. The exact mass in each shell can be model-dependent. Even so, the presence of multiple shells is robust. Nested arcs appear. Their curvature is consistent with expanding layers. Their brightness peaks along rims where path length is greatest. The 9th small unlock is that repetition supports reality. Many arcs with similar behavior point to a true layered flow. The section closes by returning to the calm ripple pattern. The arcs drift outward and broaden. Their scalloped edges soften as mixing grows. The bipolar lobes remain the larger frame that holds the archive. The wind continues to add new layers to that archive. The transition remains gentle. The next section can widen further to consequences. It can follow how repeated mass loss changes the star's remaining fuel and nudges the system toward its final phases. A star's future can be altered quietly by the mass it no longer carries. Eta Carinae's repeated shedding peels away layers and changes what remains to burn and to support itself. At this distance, the surrounding nebula looks like a calm archive. Closer in that archive implies a steady subtraction from the star's envelope. The main visual anchor is a thinning outer shroud that becomes patchy over time. It appears as a halo with brighter seams and darker gaps. The seams are denser. The gaps are clearer corridors where light escapes more directly. The halo edge does not end abruptly. It fades through a smooth gradient. That gradient is a physical detail that matters. It marks where the wind becomes transparent enough that scattering drops. The first small unlock follows. As the envelope thins, the apparent boundary moves inward. The star can shift in character without any sudden event. A checkpoint moves from the nebula back to the star's skin in plain language. The outer envelope is the star's cushioning layer. It holds heat and absorbs blows from internal change. When mass loss strips this layer, the star's core influence reaches closer to the surface. The surface then heats and brightens in different bands. The wind can also change because the surface conditions change. The second small unlock is immediate. Mass loss is not only removing weight, it is changing the star's thermostat and its wind engine. Two ideas can carry the rest of the section. The first is layered burning inside the star. The second is envelope stripping by winds and eruptions. Layered burning means different shells of fusion exist at different depths. The outer shells burn lighter elements. Deeper shells burn heavier ones. The star remains supported by pressure from hot gas and radiation. When outer layers are removed, the star can become more compact and hotter at its surface. The third small unlock follows. The same core can look like a different star when the outer coat is reduced. An everyday analogy can make the stripping intuitive and unique. The process resembles peeling layers from an onion left in dry air. Each layer removed reveals a tighter, drier layer beneath. The shape stays similar, yet the texture changes. The scent becomes sharper. The surface becomes less forgiving. In the same way mass loss reveals deeper layers with different composition and opacity. The fourth small unlock follows. The revealed layers can drive a different wind because their opacity differs. Their ability to trap light differs. Their stability differs. Another visual scene forms in the wind itself. The wind appears as a moving veil with intermittent clear lanes. Along the lanes, the central glow seems less muffled. Along the veils, the light looks milkier and spread. The pattern slowly shifts. It does not snap. It drifts as clumps move and dissolve. This shows how the star's appearance depends on the wind's thickness and porosity. The fifth small unlock is that a porous wind can mimic a thinner wind. It can allow glimpses while still carrying large mass overall. A single number can anchor how much can be removed over time without forcing precision. Over the last few centuries, the ejector mass is on the order of 10 solar masses. That is like losing the mass of about 10 suns from the outer layers. The number is rounded and spoken clearly. The scale shift stays gentle. A year is a short unit for a star. A century is still short compared with millions of years. Yet a few centuries can remove enough mass to alter the remaining lifetime. The sixth small unlock follows. A brief span in cosmic terms can change the endpoint. The checkpoint moves to what endpoint means without drama. When the star reaches its final stages, it will collapse and expel energy in a catastrophic way. The exact path depends on the core mass and the remaining envelope. A thick hydrogen envelope can produce one kind of explosion signature. A stripped envelope can produce another. The system is therefore sensitive to how much stripping continues. Another visual anchor appears in the layered shells in the nebula. The shells look like faint ripples nested around the lobes. Their edges brighten slightly. Their interiors look softer. They fade outward through gradients. These ripples represent earlier pulses of mass loss. They show that removal is not constant. It arrives in episodes. The seventh small unlock follows. Episodic stripping can rapidly change the envelope's state between long quiet phases. A limit of observation arrives softly and clearly. The interior composition cannot be sampled directly. The remaining envelope mass is inferred from models that match brightness, wind signatures and variability. Dust extinction hides the deepest regions. Clumping in the wind complicates mass loss estimates. A clumpy wind can hide mass while showing lower emission. Distance blends different zones. Different model assumptions can lead to different inferred remaining masses. This is the limit of inference. The true internal structure remains partially concealed. Even so, the direction of change is robust. The nebula shows large mass already lost. The current wind shows ongoing removal. The star is therefore evolving through shedding. The eighth small unlock is that external debris is the most honest witness of long-term loss. Another calm scene returns to the halo's shifting seams. Bright seams drift outward and thin. Darker gaps widen and then fill as new clumps pass through. The boundary between bright and dim zones remains soft. It is never a sharp curtain. This softness suggests scattering remains active. It also suggests that the wind is still thick enough to blur edges. The scale shift returns one more time. A clump forms and dissolves over days. A shell persists for centuries. A change in the envelope can steer the star's fate over thousands of years. The closing transition remains gentle and forward-looking. The next section can widen to the surrounding region of Carina. It can trace how the star's mass loss feeds and shapes the local nebula as a slowly expanding reservoir of gas and dust. A nebula can seem still, yet it is a slow reservoir that keeps reshaping the light that passes through it. Eta Carinae's mass loss feeds the wider Carina region with gas and dust that drift and mix over long time. At this distance, the star is only one source within a broader glowing field. The field is not uniform. It shows lanes, cavities and rims where density changes. The main visual anchor is a broad dust lane that curves like a dark river through a luminous mist. The lane has a sharper inner edge and a softer outer edge. Along the softer edge, brightness rises gradually through a smooth gradient. That gradient is a physical detail that matters. It marks a transition from dense dust to thinner haze. The first small unlock follows. A dark lane is not empty. It is a place where light is redirected and absorbed more strongly. The next checkpoint steps closer to the lane in a calm way. The lane is made of mixed gas and dust. Dust grains scatter and absorb starlight. Gas becomes ionized where radiation is strong. Ionized gas can glow. Dust tends to survive in denser or more shielded zones. This sets up a layered scene. Bright gas borders can wrap around darker dust interiors. The second small unlock is immediate. The brightest edges often mark boundaries, not centers. The glow outlines where radiation meets material. Another visual scene forms along the lane's rim. The rim looks like a thin, pale filament. It brightens on the side facing the radiation field. The opposite side is dimmer and more diffuse. The filament shows tiny knots spaced irregularly. Each knot has a brighter cap and a trailing softer tail. The tail fades through a gradient rather than a line. This suggests dust scattering and gradual dilution in the wake. The third small unlock follows. Knots can be denser clumps that resist erosion. They cast soft shadows into the glow behind them. Light behaves as if it is slipping around obstacles and filling in behind. The analogy stays ordinary and unique. The lane resembles cocoa powder sprinkled on warm milk. Where powder is thick, the surface looks dark and matte. Where powder thins, the milk shows through as a lighter band. Stirring does not erase the powder instantly. It makes swirls, streaks, and gradual gradients. In the same way dust and gas in Carina form swirls and streaks rather than clean shapes. The fourth small unlock follows. Mixing produces soft edges that keep memory of past flows. The checkpoint widens to the role of cavities. A cavity is a region of lower density carved by intense winds and radiation from massive stars. Within a cavity, light travels farther before being absorbed. The cavity therefore looks brighter and clearer. Its boundary looks like a curved shell. The shell is brighter on its inner face. Its outer face is dimmer and more diffuse. The fifth small unlock is that cavities act like corridors for light. They guide radiation deeper into the cloud. They also focus pressure on the boundary, which can compress gas and enhance emission. A single number can anchor the region's scale without forcing precision. The Carina Nebula spans about a few hundred light years. That is like a space so wide that light takes a few hundred years to cross it. The number is rounded and spoken cleanly. The scale shift is gentle. A dust grain responds to light in moments. A cavity boundary evolves over thousands of years. A whole nebula rearranges over millions of years. The sixth small unlock follows. Tiny processes repeated over vast time shape the large architecture. Another visual anchor appears in the glow of ionized gas. The glow is not a flat sheet. It is layered. A brighter skin lies on the side facing radiation. Behind it, the brightness drops. The drop is gradual. It forms a smooth gradient that tracks how radiation is absorbed with depth. In some places, the skin curls into a rim. In other places, it breaks into scallops. The scallops show where flow and density create uneven absorption. The seventh small unlock follows. A gradient can reveal depth in a cloud that cannot be touched. It shows how far radiation penetrates. It shows where shielding begins. The checkpoint returns to Eta Carinae's contribution. Its ejector add dust and heavy elements to the local medium. Over time, that material mixes into the nebula. It becomes part of filaments and lanes. It becomes part of the dust that sculpts light. It also becomes part of future cooling gas. Cooling gas can fragment into clumps. Clumps can eventually collapse under gravity. The story stays calm and non-personal. The eighth small unlock is that mass lost can be both an end and a seed. It ends a layer in the star. It seeds structure in the nebula. A limit of observation arrives softly and clearly. The three-dimensional layout of Carina cannot be seen directly. Many filaments overlap along the line of sight. Brightness depends on density, temperature, and dust extinction at once. A dark lane can sit in front of bright gas and mask it. A bright rim can be a near surface or a far surface. Distances within the nebula are uncertain in detail. Motion is inferred from spectral shifts and proper motion of features. Those inferences depend on assumed geometry and on identifying the same feature over time. This is the limit of mapping. Some structures are ambiguous in depth. Even so, the presence of boundaries is robust. Rims and gradients appear consistently. Cavities and lanes repeat across the field. The ninth small unlock is that repeated patterns confirm the physics. Radiation carves, dust sculpts, gas glows at interface. The section closes with a slow wide view. The dark lane curves through luminous mist like a quiet river. Filaments trace soft arcs along cavity walls. Knots sit like small islands in the flow. All edges remain gentle. Nothing snaps. The transition remains soft. The next section can widen further in time. It can follow how the nebula carries these structures forward and how Eta Carinae's long story fits into larger cycles of enrichment and change. A single star hole can alter a region for far longer than its brightest moments. Eta Carinae's debris becomes part of a slow cycle where matter spreads, cools, and eventually joins new structures. At this distance, the nebula looks like a quiet landscape of light and shadow. Within that landscape, enrichment means more than adding material. It means changing how gas cools and how dust shapes radiation. The main visual anchor is a faint expanding veil that drifts away from the central lobes and blends into the broader cloud. The veil is not smooth. It shows a soft, grainy texture, like a thin haze with slightly brighter threads. The threads fade outward through a gentle gradient. That gradient is a physical detail that matters. It indicates dilution where density drops and emission weakens. The first small unlock follows. Dilution can hide a large mass even when the glow becomes faint. The next checkpoint moves from appearance to composition in simple terms. Enrichment is the addition of heavier elements and dust formed in stellar outflows. The definition can stay short. Heavier elements are atoms heavier than helium. These atoms and dust grains provide more ways for gas to lose heat. When gas loses heat efficiently, it can become denser in pockets. Those pockets can fragment. Over long-time fragmentation can lead to new clumps that gravity can gather. The second small unlock is immediate. Adding a small fraction of new ingredients can change the cooling recipe for a whole cloud. Another visual scene forms along an interface where enriched material meets older gas. The interface looks like a faint rim. The rim is brighter on the inner side, it softens on the outer side. The boundary is not a wall, it is a blending zone. Within it, tiny filaments appear as pale strands. Each strand has a brighter spine and a softer halo. The spine suggests compression. The halo suggests scattering and diffusion. The third small unlock follows. Interfaces are where change concentrates. The chemistry changes, the temperature changes, the glow changes. An analogy can remain ordinary and unique. Enrichment resembles a pinch of salt added to a pot of cooling soup. The salt does not create a new pot. It changes how quickly flavour spreads. It changes how the surface films form as the soup cools. In the same way, added elements and dust change how energy moves through gas. They change what forms as the cloud cools. The fourth small unlock follows. The visible structure of a nebula is partly a record of its cooling pathways. The checkpoint shifts the role of dust as both shade and scaffold. Dust grains absorb and scatter light. They also provide surfaces where molecules can form more easily. Where dust is dense, radiation is filtered. This allows cooler zones to persist. Cooler zones can become denser. Denser zones can protect more dust. A gentle feedback can form without being dramatic. The fifth small unlock is that dust can help create its own shelter by enabling cooling and shielding. Another visual anchor appears as a shadowed cavity edge. The edge is a bright arc. Immediately behind it, a dimmer lane extends like a soft shadow. The shadow is not sharp. It fades through a gradient as scattered light fills in. The gradient reveals partial opacity rather than total blockage. Light behaves as if it is being sifted through a veil. The sixth small unlock follows. Shadows in nebulae often measure filtering, not absence. They measure how dust redistributes light. A single number can anchor the broader timescale without forcing detail. The enriched material disperses through the region over about 1 million years. That is like a mountain slowly wearing down over 1 million seasonal cycles. The number is rounded and spoken cleanly. The scale shift is calm. A filament can shift and fray over centuries. A cloud can rearrange over millions of years. Within that span, enriched dust can be carried by flows and turbulence. It can spread far beyond the original eruption site. The seventh small unlock follows. The star's contribution becomes less a shell and more a background ingredient over time. The checkpoint returns to Eta Carinae as one actor among many. The Carinae region hosts other massive stars. Their radiation and winds carve cavities and compress rims. Eta Carinae's ejecta enter this dynamic field. The ejecta can be swept, stretched and mixed. It can be compressed into new filaments along cavity walls. It can be dissolved into diffuse haze. Another visual scene forms where a filament bends around a cavity. The filament is brightest on its inner curve. Its outer curve is dimmer and broader. The thickness varies along its length. In the thickest part, the core looks slightly darker as if self-shielding occurs. The eighth small unlock follows. Thickness can create internal layering with a cooler interior and a brighter skin. This layering hints at how enriched material can hide inside dense strands while the glow traces the surface. A limit of observation arrives softly and clearly. The detailed chemical mix across the nebula cannot be mapped everywhere with certainty. Emission lines trace certain ions but miss neutral zones. Dust obscuration hides interiors. Overlapping structures confuse depth. A bright rim can be a near boundary or a far boundary. The mixing rate is inferred from motion and from models of turbulence. Those models have uncertainty. Small-scale clumps can survive longer than expected. They can also be shredded faster in strong flows. This is the limit of prediction. The exact future placement of enriched grains cannot be foretold. Even so, the broad direction is stable. Material spreads, gradients soften, interfaces migrate, ingredients become background. The ninth small unlock is that a nebula slowly forgets sharp events while keeping their atoms. The section closes with the expanding veil, fading into the wider cloud. Threads become softer, rims lose contrast, shadows blur as scattering fills them. The region remains structured, yet the edges relax. The transition remains gentle. The next section can resolve the arc by returning to the star's present appearance within its own debris. It can settle on the calm idea that instability and shedding are part of a larger, slow cosmic cycle. The quietest ending is often a return to what remains visible when the drama has already passed. Eta Carinae now sits inside a shaped cloud that records earlier outbursts as light and shadow. At this distance, the present looks stable. The stability is a surface impression. Beneath it, radiation, wind and dust continue to trade energy in slow cycles. The main visual anchor is a pair of opposing lobes that look like a dim lantern with two curved sides. Each lobe has a bright inner rim and a softer outer fade. Between the lobes, a darker waste pinches the shape. The waste is not a line, it is a band with a gentle thickness and a smooth gradient toward the brighter rims. This physical detail matters. A pinched waste suggests a denser equatorial zone that blocks and redirects light. The first small unlock follows. Shape is a clue to how matter leaves a star. It reveals where escape is easier and where it is resisted. The next checkpoint approaches the lobes as if they are a calm shoreline of light. The inner rims appear brighter because more radiation reaches them. The outer regions fade because density drops and scattering becomes weaker. Dust grains within the lobes filter the starlight. Filtering means the spectrum shifts toward longer wavelengths. The definition can stay short. Filtering is selective dimming by dust. The analogy follows in plain form. It is like a thin curtain in front of a lamp. The curtain does not remove the lamp. It softens edges. It changes colour balance. It makes bright zones look less harsh. The second small unlock is immediate. Dust can make a powerful source appear gentle while still shaping the surrounding space. The checkpoint moves from the curtain analogy back to the geometry of the cloud. The lobes expand. Their expansion is slow on human timescales. Yet it is real in astrophysical time. A rounded number can anchor the pace without strain. The lobes grow over about centuries. That is like a tree adding rings over centuries. Each ring is small. The accumulated shape is large. The scale shift is calm. A dust grain scatters light in an instant. A lobe changes size over centuries. The nebula around them evolves over millions of years. The third small unlock follows. The same physics repeats across timescales from grains to lobes to whole clouds. Another visual scene forms on the lobe surface. The surface is not smooth. It shows faint ridges and mottled patches. The ridges curve gently. They resemble shallow waves frozen into a shell. The patches vary in brightness. The variation forms a soft speckle that never becomes harsh. The ridges are a concrete physical detail. They hint at layered ejection or uneven density. The fourth small unlock follows. A shell can carry a history as layers even when the source is hidden behind dust. The checkpoint shifts to the idea of instability without alarm. A luminous blue variable is a massive star in an unstable phase. The definition stays short. A luminous blue variable is a massive star with episodic mass loss. Episodic means not steady. It comes in bursts and quieter intervals. Eta Carinae fits this pattern. Its current appearance is the calm interval within a longer rhythm. The fifth small unlock follows. Calm light can coexist with a history of uneven shedding. A limit of intuition arrives softly and clearly. The star itself is obscured by thick dust. The direct surface cannot be seen in visible light. The true structure of the wind is inferred from spectra, from scattered light, and from changes in brightness over time. Those inferences depend on models of radiative transfer through dust. They depend on assumed geometry. Small clumps can mimic larger smooth layers when averaged. Multiple lines of sight blend together. This is the limit of reconstruction. The exact three-dimensional arrangement cannot be known in full. Even so, the broad features remain consistent. A pinched waist implies denser equatorial material. Opposing lobes imply easier escape along polar directions. Filtering implies dust is present in quantity. The sixth small unlock follows. Certain clues survive uncertainty because they appear in the geometry itself. The checkpoint widens gently to the surrounding region. Beyond the lobes, the Carinae environment glows with diffuse emission and dark luminous lanes. Eta Carinae is embedded in that field. Material leaving the star merges into larger flows over time. The star's influence is local and also distributed through mixing. The seventh small unlock follows. A single unstable star can become part of a regional texture. Another visual anchor appears in the way light fades outward from the lobes. The fade is gradual. It forms a halo that thins into the background. The halo is not a boundary. It is a transition zone where scattering gives way to darkness. The darkness is not empty. It is simply less emissive along that line of sight. The eighth small unlock follows. Fading edges are where the mind learns to accept uncertainty as part of the scene. The section resolves with a calm synthesis of the arc. Eta Carinae is a luminous blue variable wrapped in its own debris. Its past outbursts shape a bipolar shell with a pinched waist. Dust filtering softens the light and preserves structure. Over centuries, the shell expands. Over millions of years, the material blends into the wider cloud. Instability is present, yet it unfolds on long timescales. The final visual returns to the dim lantern shape. Two curved lobes hold a quiet glow. A darker waist rests between them. Ridges and mottled patches lie like gentle texture on a shell. Light behaves as if it is moving through layers, slowing, scattering, and settling. The ending stays soft. The scene remains stable in the moment. The wider region continues its slow reshaping beyond any single event.